Let us look now into the following property, the density of the rational numbers in R, or if you want, that Q is dense in R. What does it mean to be dense for a set? So it means that if we have two real numbers, okay, let's say that X is smaller than Y, then there exists always a rational number P that is in between them. Okay, so the density means that between any two real numbers, there is always a rational number. Okay, between two reals, always a rational one. So what does this mean in practice? So you can have real numbers here. Okay, that means that in between them, there is always a rational number, but rational numbers are also real numbers. So then in between all these, we can find rational numbers. But then all these are again real numbers. So in between all these, we can find more rational numbers. You see what is happening? Let's do one more time. So let's say all these real numbers, we can find rational numbers in between. So what does this mean? That means that in the real line, the rational numbers are everywhere, okay? Wherever you look at, you will have infinitely many rational numbers completely intertwined with the rational ones. Okay, so that's the density. Now, let's look into the proof. So in this case, we are going to do a constructive proof. So we are going to show that we can construct that rational number P. Okay. Notice here that I'm saying the numbers X and Y are real. They could be rational or irrational. Okay, so let's go for it. So first thing, notice that Y minus X is bigger than 0, okay, because I'm assuming that X is less than Y. Okay, sorry. And then we have the Archimedean property that we saw in the previous video. Okay, that says what? We have a positive number here. So the Archimedean property said that if we multiply enough times a positive number, we can get something greater than any other number that we choose. So in this case, we choose 1. Okay, so what we are saying here, we choose 1 because it's convenient. You will see later. It says that there exists a number n such that, let me create some space there. Such that n times y minus x is bigger than 1. Okay, this is the Archimedean property. Again, remember in the Archimedean property, we needed to pick. This was the y, and this was the x bigger than 0 in the Archimedean property. Okay, so if you want to go back to check, you can pause the video, check it out, come back. Now, this we save for later. Now, the Archimedean property also says that there exist numbers m1, m2, okay, natural numbers, positive integers, such that m1 is bigger than nx and m2 is bigger than negative nx. So in this case, what are we doing here? In this case, we are taking x in the Archimedean property to be 1, okay, which is positive, of course, and y, we are taking either nx or negative nx. Remember, in the Archimedean property, we said that x needed to be positive, but we didn't say anything about y. Okay, so here we have these two inequalities. From these two, what we have is that nx, let's flip the second inequality, multiply everything by -1, -1, so that we have that nx is in between negative m2 and m1. Okay, so we are saying that nx lies between two integers. All right, but so the picture we have in mind, the picture we have in mind would be something like this. Okay, like really a tight bound. What we are saying here is actually something more like is 0. So we would be saying something like from here somewhere else. Okay, so we have a bound that is negative m2 and m1. It's a bound. It lies between two integers, but it's not tight. Okay, so the next thing we can do is, okay, let me tighten the bound. Okay, once we know it's in between two integers, we can make it as tight as possible and say, well, yeah, for sure I can tighten it from both sides and get that there is some m in the natural numbers such that m minus 1 less or equal than nx less than m. Okay, here we are tightening the bound. All right. There we go. So this is what we wanted. Okay, this I'm also going to save for later. But one thing that we want to notice here, so if we have our m minus 1 and then m, okay, on both sides of nx, something else that we can know for sure is that if I add 1 unit to nx, I'm going to be on the right of m, by the way this is defined, okay? Just add 1 unit here if you want. You would be m less or equal than nx. Well, yeah, plus 1 less than m plus 1. We don't care about this part. This is what we want. Okay, m less or equal than nx plus 1. And now we look at everything that we have so far. So let me copy. Let's continue here. All right, so there we go. That's all we need. So let's call the first, well, let's just number them so that we can track the argument and forget about what we did. This is the byproduct that we needed from before. Okay, so now let's follow the chain of inequalities, okay? So for example, let's start with number 3. Okay, and notice that M appears also in number 2. So we can right away use it. Okay, so we have that M is in between NX and NX plus 1. And then what else can we do here? Yep. So if we look at number 1, we can rewrite it, right? Ny minus nx bigger than 1, that's number 1. So if we move nx to the other side, what do we get? That nx plus 1 is smaller than ny. And now let's look at these 3 closely. We have nx less than m less than ny. And finally, if we divide by n was assumed positive. Okay. Oh, what happened there? Okay, so this is less than y. We have our rational number p. Okay, so that's how you show it. Notice that this was a constructive proof because we started from the hypothesis we had and we constructed the rational number p.